How is everyone today? How are y'all doing? Doing pretty good myself. Good to hear. Alrighty. All right, kind of want to cover a lot today, so I'll go ahead and get started. So I'm going to do one more example of Stokes' theorem, because divergence theorem is honestly a lot easier to kind of understand and work with, in my opinion. And Stokes' theorem is where people tend to have the most trouble, and it's kind of the most labor intensive. So let's do another Stokes' theorem example here. All right. Okay. So let me just draw a picture, because it really doesn't matter exactly what the shape is so much, as we'll see. My goodness. All right. So we're going to let C be the unit circle in the XC plane. So if we just project to the XC plane, if we look at it here, it's our good friend, the unit circle here. So that's C. So pretend that's our unit circle. Pretend that's in the XC plane, lies in the XC plane. So S1 and S2 are going to be two halves of a closed surface, and they can be literally whatever. But they're both going to share the boundary. Each of these pieces are going to share that boundary, C. So let's say this is S2. And let's say this is S1. And the two together have outward pointing. So if we consider them together, the union of the two, let me do this a different color. They form a closed surface, and that closed surface we're going to give the outward orientation. Oh, come on, don't do that. All right. Okay. Okay, so I'm going to rely on this picture rather than writing all that down, and I hope that's somewhat clear. But S1 and S2 are just two halves of a closed surface, and they share the boundary C. Each of those surfaces have boundary C. Boundary curve, well, we'll talk about orientation in a second. So that's our C, and then our vector field F is going to be y plus C sine xy and e to the xyz. Okay, so what we want to do is we want to calculate the flux of curl of that vector field across each of S1 and S2. So we're going to calculate the curl, the flux of the curl of F across S1, and then we're going to calculate the flux of the curl of F across S2. Okay, so let's try to figure out what we're doing here. Okay, so what we want is, so the flux of a vector field is just the integral of that vector field over the surface. So we want the integral over S1 of the curl of F, and also the integral over S2 of the curl of F. So we want both of these. Okay, so one thing should be screaming out to you. If not now, it should be when you get some practice. If you see the integral over the surface of a curl of F, that should be screaming out, use Stokes' theorem to you. If you see integral of curl of F over a surface, that is telling you automatically use Stokes. Several exclamation points after that. Okay, so by Stokes, so let's just focus on S1 for now. I will bring S2 back in a sec. So by Stokes, the integral over a surface of the curl of F, the derivative, integral over surface of the derivative, is equal to the integral over the boundary curve of the vector field F. So that's going to be equal to the integral over the boundary of S1. So the boundary is the curve C, but we need to give it an orientation. To that guy before we proceed, of, instead of the curl of F, just the vector field. So that's the integral over the first piece. And we'll get to the second piece in a sec. We'll see there's a nice shortcut. Okay, so let me erase this again. So let's figure out the boundary, the orientation for the curve C when it's considered as the boundary of S1. So we could do our point your head in the direction of the normal, stand on the curve and walk along it so that S1 is always on your left. Or we could just use the right-hand rule because S1 only has one boundary curve. I'm going to use the right-hand rule because I like that. So I'm going to take my right hand, point my thumb in the direction of the normal. In general, it's pointing towards the negative y. And then curl my fingers inwards, and that will give me the orientation along the boundary curve C. So when I do that, if I'm looking at it from the positive y direction, am I going around clockwise or counterclockwise? Right, so if I'm looking at it from the positive y, I'm going around in that direction. Does everyone see that? So if we drew this, we'll draw this in the XZ plane just to see better. So we're going from the positive x-axis to the positive z-axis. So we're going around this way. And I will redraw that on the, there we go, on the next page. Okay, so here is our dude in the XZ plane, unit circle, and on the unit circle we're going around, oops, counterclockwise. Go back to this. I kind of erased all the directions and stuff. The next one? Okay. Okay. Alrighty. So we need to parameterize our curve. Oops. So that's our curve C. Let me just draw it in here to emphasize. Right. Okay. Okay, so our curve, if we're looking in the XZ plane, just this bit here, just pretend it's like X and Y, except it's the XZ plane. Okay, so our curve lies in the XZ plane. What does that tell us about Y? It's equal to 0, right? Y equals 0 is the XZ plane. The curve lies entirely inside the plane Y equals 0, so Y is going to be 0. Okay, so for X and Z, we're going around counterclockwise. We're the unit circle. And so we let the horizontal guy be cos, the vertical guy be sine, because we're going around counterclockwise. So X is cos t, Z is sine t, and then we just let t go from 0 to 2 pi, because we're going around once, one full revolution. So that's our parameterization. Since we're integrating a vector field, we're going to need our prime of t. So our prime of t is just going to be negative sine t 0 cos t. And just a reminder, f is going to be, I think it was y plus c. Yep. So y plus c sine of xy, and then e to the xyz. Okay. So replacing x, y, and z with their parameterizations in f. So t goes from 0 to 2 pi. So f, y plus c sine of xy e to the xyz. Replacing x with cos t, y with 0, z with sine t. So y plus c becomes 0 plus sine t. Sine of xy becomes what? 0, right? Sine of cos t times 0, which is sine of 0, which is 0. Seriously. And e to the xyz becomes e to the 0, because y is 0, which is just 1. And then we said our r prime of t was negative sine t, 0 cos t, dt. And so we get the integral from 0 to 2 pi of negative sine squared t plus 0 plus cos t. And this is a straightforward integral to calculate. Cos t integrates to 0, just sine t evaluated at 2 pi and 0. Negative sine squared t, we do our negative, then 1/2, 1 minus cos 2t. And then when we integrate, we see we get negative pi when we evaluate that. Okay, so that's the S1 bit using Stokes. So that's the flux of the curl of f over S1. Oops. Okay, so that's half of this. The other half, we're going to use a nice shortcut to save ourselves from doing all this work again, essentially. But does everyone see how we use Stokes' theorem on just S1 to get this? Instead of integrating curl of f over S1, we integrated f over the boundary curve. So you parameterize, et cetera, et cetera. Okay. So we're not actually going to do any calculation for this one, and here's why. Let's look at our picture here. So S1 and S2 together, if we put this whole thing together, let's call it S. So S1 union S2, if we put the two together and consider it as a single surface, as two pieces of a single surface, it's a closed surface with outward orientation. As we'll see, that's not super important in this case, but we have a closed surface. Okay, so it's a closed surface. So what do we know about the integral of the curl of a vector field over a closed surface? Once again, Ryan with the 0. Exactly. Lots of zeros going on here. We know the integral over a closed surface of the curl of a vector field is 0, because Stokes' theorem tells us we can just integrate the vector field over the boundary of S, but the boundary of a closed surface is empty. There is no boundary of a closed surface. So we're integrating something over nothing, which is 0, essentially. So we know the integral over the two pieces together is 0, but the integral over the whole thing is just the integral over S1 plus the integral over S2. Right? That's how we integrate over a piece, over multiple pieces of a surface. And we just calculated the integral, the flux of curl of f over S1. That's negative pi. And we want to know now the flux over S2. So we know negative pi plus the flux over S2 is 0. So then the flux over S2 of the curl of f has to be positive pi. Because when you add it to negative pi, it has to be 0. If we wanted, we could have played the same game we did as the last one, but we've already basically done all the work. And we use our knowledge of Stokes' theorem, namely the integral of the curl of a vector field over a closed surface is 0, to make our lives easier here. And once again, the interesting thing here is it literally doesn't matter what S1 and S2 are. As long as they have C as their boundary, right? And that is a consequence of Stokes' theorem. If you integrate a derivative over a region, the derivative being curl of f, it doesn't matter what that region is. All that matters is the boundary of that region. So any surface that has C as its boundary is going to have the same integral. Keeping in mind the orientation here, because these two guys have C as the boundary, but the orientation, if we look at it, is opposite for each one. But the point is, the shape of S1 and S2 don't matter. All that matter are their boundary, because we're integrating curl of f over them. Okay. Any questions about that? And that'll close out Stokes' theorem. Let me see. Did I want to? No. Okay. All right. Let's look at the final bit of new material in the class. And that is our last integration theorem. Possibly the easiest. Well, maybe tied for the easiest. And that is divergence theorem. Okay, so we've been introducing all of these guys as kind of discrete, separate theorems, and you have to look at the situation if you have a problem to figure out which theorem you're going to use. But really, honestly, they're actually all the same theorem. If you use kind of a more abstract setting, but really they're all saying the same thing. Pretty much every integration theorem in calculus boils down to the following. It's basically the integral of the derivative of something and what derivative means varies depending on the thing we're integrating. Could be just the normal derivative. It could be the gradient. It could be the curl. It could be the divergence. But they're all just a derivative of an object. So the integral of the derivative over some region is equal to, is interchangeable with, the integral of the thing, not the derivative, the thing. So the integral over the oriented boundary. And that is every single integration theorem you've ever learned in this class, going back to 140. And I'll show you some examples. So you can either integrate a derivative over a region, or you can integrate the derivative of a function over a region, or you can integrate the function over the boundary, the oriented boundary, as we'll see. The two are the same thing. They're equal. So the fundamental theorem of calculus, FTC, as I call it for short, is the very first one you learn. And that's in 140. So we can integrate a derivative, f prime of x. Well, first of all, let's look over at our region of integration. So we're looking at a function of one variable, and we're integrating over an interval on the real line. So from A to B. So if that's our I, that interval, the oriented boundary of I is going to be the endpoints, but we give it an orientation, right? Hang on. So the point B minus the point A. So that's the oriented boundary of I, right? And I'll write it down, and hopefully this will make more sense when I write it down. So this, in this context, we can integrate over the region I. So from A to B, we can integrate f prime of x. Oops. So that's equal to the antiderivative. So f at B minus f at A. So this is the integral of the derivative over the region I, the interval, on the left-hand side. And on the right-hand side, we're evaluating the function, not the derivative, on the boundary. So at B, it's positive. At A, it's negative. So this is evaluation at points is just a zero-dimensional integral. You don't need to concern yourself with that too much. But really, this is the integral over the boundary of f. So the integral of the derivative over an interval is equal to the integral of the function over the oriented boundary. So that's why it's f of b minus f of a, because the oriented boundary is the endpoint b minus the starting point a. So that's how we put the fundamental theorem of calculus in this setting. And then super quickly, fundamental theorem of line integrals. So we have some curve C, and we're going from point P to a point Q. So if that's our C, then our oriented boundary of C is going to be the endpoint minus the starting point. And so this same theorem, right? Integral of the derivative over a region is the integral of the function over the boundary, oriented boundary. And so we get the integral over the curve C of the gradient of a function So if we integrate a vector field, which is conservative, right? That means it's the gradient of some function. So we could just write it as the integral of the gradient of a function. That's equal to the integral, that's equal to the potential function, the antiderivative, at the endpoint minus the antiderivative at the starting point. And this is the same thing. Integrated derivative over a region, a curve C, that's the same as integrating the function, not the derivative, on the oriented boundary, f of q minus f of p. And then I'll skip grains, it's like the same as Stokes, but in the interest of time. But just a reminder, Stokes is the same thing too. If we have a surface S, so we give it an orientation. If we look at the boundary curve or boundary curves, and we give that an orientation, the oriented boundary. So doing our right-hand rule, this would be oriented in this manner. Stokes says we can integrate the derivative over S. So curl of f is our derivative in this case. Or we can integrate the function, the vector field in this case, f, over the oriented boundary. Integral of the derivative over a region, a derivative of a function over a region, is equal to the integral of a function over the oriented boundary. Okay, so that brings us to divergence theorem. So let E be a solid region in R3. So a solid three-dimensional region. And the boundary surface, right? If you have a solid region, the outside of that surface is going to be a closed, outside of that region is going to be a closed surface. So E is a solid region. S is the boundary of E. It's going to be some closed surface. And we're going to give it the outward orientation. So it's a closed surface. So the normals can either be pointing out or in. And we're going to give the normals the outward pointing orientation. So following what we've done before, we can integrate. So our function here is going to be a vector field. So we can integrate over the solid region E the derivative of the vector field, in this case, the divergent, me say, so for vector field F, we can integrate the divergence over the derivative over a region, or we can integrate the function, in this case, the vector field itself, over the oriented boundary. So that is the outer boundary surface with outward orientation. So we have the integral of the derivative over some region is equal to the integral of the function, not the derivative, over the oriented boundary. The boundary being just the outer surface given the outward orientation. Okay. So this, one thing I want to emphasize, I saw a bunch of people on quiz 2 trying to use divergence theorem, which you could, but you have to be careful and you can't use it directly for 2 reasons. So if we're given, usually the way this goes is we're given a surface integral over a closed surface, right? The integral of a vector field over a closed surface is what we usually start with. And we usually use divergence theorem to turn that into a triple integral over the enclosed region of the divergence of the vector field. But I want to emphasize, you need to have a closed surface in order for this to work. In the quiz, our surface was not closed, right? Our surface was only the top part of this paraboloid. If you wanted to close it, you would have to include this bottom piece here, which you could do. There's a clever way to do it, but it doesn't work directly. And also you have to be mindful of orientation, because in the problem, our surface had downward pointing normals. And if we close the bottom, turn it into a closed surface, that would be inward pointing normals. So the sign would be wrong here, right? We would have to make this negative and switch to outward pointing normals in order to directly apply divergence theorem. And so you would have to put a negative on the other side as well. Just wanted to mention that quickly. Okay, so let's do a problem as quickly as we can. So let's verify the divergence theorem for the vector field F, which is y. Let me remind myself what this is exactly. Yz, z squared, and here E is going to be the solid cylinder. So x squared plus y squared less than or equal to 4, and z goes from 0 to 5. Oh, okay, so when it says verify, in integration theorem, it means do both integrals and show that you get the same thing. Okay. So E is the solid region, three-dimensional region. So it's x squared plus y squared less than or equal to 4. So it's going to be the region inside the cylinder, x squared plus y squared equals 4. And so that's a cylinder of radius 2, centered on the z-axis. And z is going to go from 0 to 5. So that's z equals 5. And so the outer piece is going to be the circle x squared plus y squared. If you project down to the xy plane, x squared plus y squared equals 4. Circle centered at the origin of radius 2. So E is a solid region. S is going to be the outer boundary of this guy, given the outward orientation. Okay, so I want to emphasize, you need to be careful here. Now, for Stokes' theorem, this is an easy mistake to make. I'll mention this and then we'll come back to it when we do the surface integral. So the boundary of this solid region consists of 3 pieces. It's easy to forget about the top and bottom surface. But we have, we'll say S1 is the cylindrical part, the sides, with the outward orientation. We'll say S2 is the top piece, and that is going to have upward pointing normals because the whole thing together has outward pointing normals. And let's see, S3 is the bottom piece, and that's going to have downward pointing normals because the whole thing. Z component is 5. Well, it depends on which piece we're talking about, as we'll see, Terrell. But on the top, yes. But we'll get there. So let's do E really quickly. So we're doing 1/2 of divergence theorem. So the integral over the solid region E of the divergence of our vector field. So the triple integral of divergence of F. So remember, divergence of a vector field is a scalar function. And so we're doing the triple integral of a scalar function here. This is what we're calculating. So first of all, what's the divergence of F? Well, F is y, yz, z squared. The divergence is going to be the derivative of y with respect to x, which is 0. Exactly. Plus the derivative of yz with respect to y, which is z. Plus the derivative of z squared with respect to z, which is 2z. So we get 3z as our divergence. That's our integrand. Okay, we're integrating over the solid region E. So we have a triple integral. How do we want to do this? So we could use cylindrical, spherical, or rectangular coordinates, which is most appropriate here. Right. So let's use cylindrical, in particular about the z-axis, but that's the usual one. So we're using cylindrical, and we need to find the bounds for E. Well, R, projecting down to the xy plane, we see R goes from 0 to 2, theta goes from 0 to 2 pi, and we're told Z goes from Z equals 0 up to Z equals 5. And so let me write our bounds. We get the integral. Theta goes from 0 to 2 pi. R goes from 0 to 2. Z goes from 0 to 5. So this is a triple integral. Keep that in mind. Of the divergence of F, which we said was 3z. But we need to change our function 3z, we need to replace x, y, and z with their cylindrical equivalents. Well, luckily, z is equal to z in cylindrical coordinates. So that remains 3z. And then what does dv become in cylindrical? Right, we can't forget the r, right? So it's r dz dr d theta. So we're integrating 3zr dz dr d theta. That's a pretty easy integral. Really nothing tricky there. When we evaluate it, we get 150 pi. The evaluation's not the part we haven't seen before. It's making sure we set everything up correctly here. Use cylindrical, et cetera, et cetera. Okay, so when we do the integral over E, the solid region of the divergence of f, we get 150 pi. Now let's look at the integral over the boundary. Let's call the whole outer boundary S. So for divergence theorem, we're integrating over the closed boundary surface, outwardly oriented, of the vector field itself. Also, let me mention, often you might see this notation. I don't think the book uses it, but you might see this notation sometimes. Because it's a closed surface, they'll put a circle in there like they do when we orient. So when we do line integrals over closed curves, we'll put the circle there. They'll do the same sort of thing for integral over closed surfaces. So it's a double integral with the circle thingy there. That's some notation you might see. I don't believe the book uses it, but you might see that. Okay, so just redrawing our guy. We said S consists of 3 pieces. S1, which is the cylindrical piece with outward oriented normals. S2, the top piece with upward pointing normal. And S3, the bottom piece with downward pointing normal. We have to do this as 3 pieces because we can't parameterize all 3 surfaces in one go. Okay, I'm gonna power through this really quickly. Okay, so S1. The cylindrical part, the outer surface is the piece of the surface x squared plus y squared equals 4. Z goes from 0 to 5. So we're doing the cylinder part. And so we're going to use cylindrical coordinates to parameterize. But when we do surfaces, so cylindrical coordinates has r, theta, and z as parameters. We need to get rid of one of those. So we need to write the equation of the cylinder in cylindrical coordinates. And then that tells us what we're replacing one of the variables with. So x squared plus y squared equals 4 in cylindrical. That surface is r equals 2. And so r is gone now, and we're left with theta and z. And so we get x's, instead of r cos theta, it's 2, because r is 2, cos theta. Y is 2 sine theta, instead of r sine theta. And z is still z. And theta goes from 0 to 2 pi, because we're going all the way around the z-axis. And z, we said, goes from 0 to 5. Okay, and so this is a tricky bit, slightly tricky. We're integrating a vector field, so we need either g theta cross gz or gz cross g theta, well, plus or minus g theta cross gz. We got to figure out which one. So let's do g theta cross gz. I'm basically just going to tell you what it is. We can figure that on our own, I'm sure. And then we're going to see if that gives us the right orientation. If not, we need to do negative of that. So g theta cross gz is going to be 2 cos theta, 2 sine theta, 0. Okay, so it's kind of hard to, we can't describe the normals for the side as being pointing like in the negative, the positive or negative y direction or the positive or negative x direction, because we have normals that point in all those ways. But what we can say is we have basically the normals are going to be pointing radially outward. Right, so if we look at our point on here, and we look at from the z-axis, the vector pointing towards that point, the normal on the surface is going to be pointing in the same direction as that guy. So if we look at this guy here, the normal there is going to be pointing in the same direction. So we look at the radial guy. And so basically, if we sort of ignore z, and just see which of g theta cross gz or negative of that points in the same direction as this guy, looking at the x and y coordinates, that's our guy. I don't want to dwell on that too much. It's takes a bit of explaining. But this 2 cos theta, 2 sine theta, 0 is going to be the guy we're looking for. Because the negative of that is actually going to point in the opposite direction. Okay. So super quickly. The integral over S1 of our vector field. So remember, F is going to be y z squared. So we said theta goes from 0 to 2 pi, z goes from 0 to 5. Our vector field F, y z squared, replacing x, y, and z with their parameterizations. Y becomes 2 cos theta. Yz becomes 2z sine theta. And then z squared just becomes z squared. And we're dotting that with 2 cos theta, 2 sine theta, 0. dz d theta. And when we take that dot product, we get 2 cos squared theta. Nope, sorry. This is 2 sine theta. Sorry, it's not x, it's y. Nope. So we get 2 sine theta cos theta plus 2z sine squared theta plus 0. Yes, 4. Sorry. Yep. Trying to go too quickly here. Yep, 2 times 2 for each of these. Yep, so they're both 4. You're right. And we should be able to evaluate that. We get 50 pi from this piece, from the sides, S1. This is just the cylindrical side, the sides. We also have to do the top and bottom. Those are going to be really quick, really quick. But from the sides, we get 50 pi. We're going to have to add all these up together at the end, but let's do that. Super quickly. S2 is going to be the top with upward orientation. Okay, so there are different ways to do this, but here's, I think, the easiest way. So this is the piece of a piece of a plane. In particular, the plane z equals 5. Right, so we're looking at the piece of the plane, z equals 5, where x and y live in that region D, the projection down to the xy plane. So z equals 5, that's the graph of a function, just the constant function 5, because we got z by itself. So we're going to let x be x, y be y, and z be 5. And our bounds for x and y are just they live in that region D. We're just going to leave it at that for now. Okay, so the normal, our function is just a constant 5. And so remember, for the graph of a function, the upward pointing normal is just going to be negative derivative of that function with respect to x, negative derivative with respect to y, 1. And we want the upward pointing normal, so that is good. The derivative of a 5 with respect to x is just a constant, so that's 0, 0, and then 1. A reminder, we want this because it's upward. Why do you do this, dude? Thank you. So the integral over S2 of our vector field is going to be the integral over D. And we're going to replace x, y, and z with their parameterizations in the vector field. So y, z, z squared. Y is still y. Z is 5, so yz becomes 5y. And then z squared becomes 5 squared, which is 25. And dot the normal, which is 0, 0, 1. dA, because we're just integrating over D, we haven't given bounds yet. So when we take the dot product, we get the integral over D of 25 dA. And we can interpret this in terms of area, because it's just a constant. So this is 25 times the area of D. And D is just the the disk of radius 2. So the area is pi times the radius squared, 4 pi. So we get 25 times 4 pi, which is 100 pi. Okay. And then S3 is going to be very similar. I'm just going to blaze through this and really not actually do it. You should be able to see pretty quickly what happens. If we look at S3, it's the same as S2, except now we're in z equals 0. So we let x be x, y be y, z be 0. Sorry, not z, 0. X, y are going to live in the same region D as in S2. And the normal is now going to be the same thing, but it's downward pointing, right? So we get negative g sub x, which is 0, negative g sub y, which is 0. Or sorry, positive g sub x, positive g sub y, negative 1. And then it turns out when we take our vector field, y, yz, z squared just becomes y, 0, 0. And we're dotting that with 0, 0, negative 1. So we're integrating 0. Over the region D, so we get 0. So the integral over the boundary is the integral over S1 plus the integral over S2 plus the integral over S3, which is 50 pi plus 100 pi plus 0. We get 150 pi again. Okay, my apologies. That went a lot longer than I intended. Any questions about divergence theorem or anything? We'll be doing more examples tomorrow. All right, then I will see you guys tomorrow, and have a great rest of your day.
Can I ask a quick question about the homework?
Sure.
You want me to pull it up?